Greetings, AP Calculus students. Mr. Record here. We're looking at our second video in the series of solving differential equations, but now we're going to turn our attention to an application. And that application is of growth and decay. There's so many times in the real world that we find that the rate of change of a variable y that is to be directly proportional to the value of y, just as you read here from the slide, which is just really another way to say that the derivative of y with respect to time is equivalent to some constant times y. And you're going to find that this drives a lot of our basic growth that we're going to encounter. There is a little bit more realistic version of growth that deals with human populations and other life populations that pertains to pertains to logistic growth, which is actually a BC topic. But for the purpose of just introducing this, we're going to stick to this really basic relationship. And if you look here in the box, it kind of gives you the growth and decay model theorem. If y is a differentiable function of t and y is positive, and we know that this derivative relationship up here is intact, then we could then say that that y is just going to be equivalent to some constant c times e raised to the kt power. Sometimes we affectionately call this kect. C in this particular case will be the initial value of y, so the initial amount of the material. K is just some proportionality constant. K is sometimes hard to grasp, but it's just some value that pertains specifically to the situation at hand. And if that K is positive, we experience growth, and if that K is negative, we would experience decay. Now, before I begin with a full-blown example, I want to revisit that differential equation, that dy dt equaling k times y, because we see that ultimately this is going to beget this equation kect. And that's really important because it turns out that we're going to be able to find a lot of information. We're going to be able to find how much of this particular material there should be at a given time, or it's possible that vice versa could be the case, and we would know how much we would have, but we're supposed to figure out when that's going to occur. But in either situation, if we're starting with this particular relationship, we're going to have to undo this derivative. We're going to have to solve this differential equation. And if you watched part one of my series of videos here, you'll notice that we did indeed introduce a topic called the separation of variables, and we proceeded to solve a differential equation. So we're going to do the same thing here. We're going to decide that it's going to be best for us to get y's on the left side, and we're going to get this t, or this dt, instance over to the right side. So I'm going to begin by dividing both sides by y and multiplying both sides by dt. Now at this point, we can then take the antiderivative of both sides of the equation, which would produce on the left side. The antiderivative of 1 over y is the natural log of the absolute value of y. And on the right side, the antiderivative of k with respect to t, where k is a constant, would be k times t, and then I'm going to move any constant that may have been left on the left side and any constant that would come about on the right side, mix them together as a single constant c, and I'm going to put that on the right side. Now, we're not quite to the point where we can say what y is equivalent to, so one means by which we could do that is we could use each side as exponents of the base e. And upon doing so, we would have that the natural log and the e dissipate, and we're just left with the absolute value of y. And then on the right side, I'm going to kind of slow this down a little bit and remind us of a very important exponential property that says whenever you are going to multiply two like bases, we could, in essence, add the exponents together. So we're just kind of moving in the opposite direction of that particular algebraic principle. And then at this point, we see that this e to the c is just in itself a constant that I'm going to call c. Now, because of that, I might give this constant up there some kind of a subscript so that we know that he's not necessarily going to be the same as the c that's produced here. So at this point here, we would have our c times e raised to the kt power. And on the left side, for this particular video, I'm just going to go ahead and remove the absolute values. I know that that's a little bit of a daring move in this part because we really don't know what the value of the c is. However, we do know that if you take e and you raise it to some kind of a power, we know that that's going to produce a positive result. The instance of deciding on the sign of y is going to become a little bit more clear whenever we have specific examples and actual data values for t and y. But that's how we can achieve that particular result. Now I'm going to finish up with a very quick example here, number 2, where we can actually put this to use. We're told that the rate of change of y is proportional to y. Now, the whole goal of me showing you that previous information is that whenever we see this information, we can immediately write our Keck equation, if you will. There really is no point in solving the dy over dt equal to k times y over and over again if it's going to produce the same result. So we're going to be able to save a great deal of time. And then from this point, what we're going to have to do is we're going to have to proceed to find the value of c and the value of k. So we'll find c first. Finding c can be quite easy if you look very specifically at the data shown. In this case, when I have the t equaling 0, that's going to indicate that the initial value of our y would be 2. So we know that this c has got to be 2. But if we forget that, no harm is done, because if we just proceed to implant 0 for t and 2 for y, what we'll end up with is the equation 2 is equal to c times e to the 0 power, which is the same as 1. So there it is, c is equal to 2 nonetheless. So now we know our equation for y is a little bit more specific, 2e to the kt. Next up, you guessed it, it's all about finding k. Now, in order to find k, you're going to have to be given some other information, and lo and behold, we do have that. We have another relationship between t and y that isn't necessarily the initial relationship. So in this case, we're going to go ahead and let y be 4. At the same time, we let the t value be 2. This will enable us to solve for k. So if we divide by 2, we would end up at this point. And then we would have to proceed in taking the natural log of both sides of this equation. Of course, that will free up this 2k and allow it to come out in front of the natural log. So we do that. And then there's really no need to write the natural log of e because we know that is equivalent to 1. So in one last step, we'll divide by 2. We can write that a couple of different ways, but I'm going to call it 1/2 times the natural log of 2. So that would serve as our k. So what does this mean? Well, now we have a much more complete and very reliable equation for y. We are going to replace the k with the 1/2 ln of 2 times t. And we now can do a variety of things with this, not one of which is answering the question, what is the value of y when t is 3? That's just basically asking to find y of 3. So we can proceed with that. And upon doing so, we have something kind of interesting here. We've done pretty well with this problem. We haven't used a calculator just yet. And I think that we're still going to be able to maintain that particular attitude with this question, but you're going to have to be very careful with this. And I very carefully placed the natural log of 2 in the parentheses there to kind of indicate that the coefficient of the natural log of 2 is really deemed to be 3/2. What that will mean is that this 3/2 can in turn become the exponent of the 2 after the natural log. Now, the reason why that's important is because we have a rule that says that an e base raised to the natural log of some quantity, some expression, will be equivalent to that expression. I don't want to say that the e and the ln cancel each other out. That's really not what's going on, but they sort of dissipate and just leave the value that's left behind, which in this case is 2 raised to the 3/2 power. And then, of course, if we work on this just a little bit more, the square root of 2 is 4, I'm sorry, 2 to the 3rd power is 8. Let's do it that way first. 2 to the 3rd power is 8, and then this 2 in the bottom is just really the cube, the square root, that is, of that 8. And of course, we could rewrite this as 2 times 2 square root of 2, or 4 square root of 2 after all is said and done. And that's what the value of y would be at that specific instance. Now, we do have a graph over here that I've kind of put together before the fact, just to kind of reiterate some of these things that are happening in this particular relationship. We have the point 0.02 that lies on the curve. We have the 0.24 that lies on the curve. Now, as far as the point where the t is 3, we have this value up here that's just a little bit tougher to kind of figure out because he's a little bit bigger than 5, not quite as big as 6. Well, he's going to have the value 4 square root of 2, which is going to lie between the 5 and 6. So the graph does sort of back up our findings. So anyhow, this is it. This is your first really application type of growth and decay. In the future videos, of which there are 4 or 5 more that follow, you're going to see very specific applications that pertain to different phenomenon that are existing in the real world. Anyhow, I hope this helps, and I hope to see you at the next video.